Yeah, good morning my dear students. Today we are going to discuss about various detectors used for UV visible spectrophotometry. So what are these detectors used for UV visible spectrophotometry? Basically the detectors are used to get the transmitted light radiation, which is used to convert the light energy into electrical energy. So the very important detectors, these detectors are also called as photometric detectors. The first important detector is a barrier layer cell or photovoltaic cell. So how this detector is working? Basically we have the outer coverage layer, which is basically acting as a cathode, which is made up of noble metals like silver, platinum and gold, and inner metallic layer is made up of copper or iron as the metallic layer, and in between there is a semiconductor layer of selenium, which is either made up of copper oxide or selenium oxide. Now what will happen basically, and this is connected electrically with the resistance, and through the help of galvanometer this is entirely connected in this manner, right? So now this barrier layer cell, barrier, what is the meaning of barrier? Because this central layer is the barrier, which is basically a selenium layer, and this layer will not allow any movement of electrons in this layer, because selenium is a metal which is having the low electrical conductivity, so it will not allow the electrons to move from one place to another place. So the electrons mobility will be very low in case of selenium layer. So now what will happen? When I pass the light radiation, when the light radiation is basically the transmitted light radiation, when it is hitting the detector and when it is hitting the cathode, and then when they are going towards the selenium semiconductor layer, so immediately what will happen? It will sensitize the selenium layer, and once the light radiations falls on the selenium layer, the electrons will become mobile. The electrons will become mobile, and that is taken up by the metal layer, which is positive as such, and therefore the radiation, the electrons will be moving from this terminal to this terminal. So during the movement of electrons, what will happen? It creates a potential difference between the two electrodes, and that causes the flow of current, which is giving a signal in the galvanometer needle. So this is how the barrier layer cell works basically, and it is a very preliminary based detector used for calorimeter as well as some spectrophotometers. But basically barrier layer cell is having lot of disadvantages. Even though it is inexpensive detector, we cannot apply the high external resistance in the barrier layer cell. That is a disadvantage of the barrier layer cell, right? So this is how the barrier layer cell is working. I hope it is clear. Now coming to the second important detector, that is called phototubes. What do you mean by phototubes? These phototubes are also called as photoemissive cells. The phototubes are also called as photoemissive cells. So here the light radiations are passing through the quartz window through an evacuated bulb, and they are hitting the photoemissive cathode. This is basically a cathode. When the light radiations are the photons, basically the most of the UV radiations are photons. The photons are converted into electrons, or light energy should be converted into electrical energy. That is the purpose of any UV visible detector. Now what will happen? The light radiations, when they are hitting this photoemissive cathode, the photoemissive cathode is coated with some special substances like cesium, cesium oxide, silver or silver oxide, or potassium. So all these elements belongs to group 2A of the periodic table, right? So when we are having these elements, they are emitting. What will happen? These photoemissive cathode, that means once the light radiations are hitting, the photons are hitting the cathode, they will try to emit the electrons, and these electrons are captured by the anode here. So when the electrons are emitted in the cathodic terminal, there is a movement of electrons towards the anode, and this movement of electrons towards the anode causes the flow of current, and that will be easily sensitized by the galvanometer needle. So this is how the difference in flow of current can be easily identified from cathode to anode terminal, right? So what is an advantage of phototubes? Phototubes can be used in spectrophotometer. They are better than the barrier layer cell in terms of sensitivity, and they are more better as such. In most of the modern instruments we are using phototubes only as such, right? Now the next important detector what we are going to discuss is photomultiplier tubes. That is very important in case of double beam spectrophotometer, that we are going to discuss it now, right? So what is this photomultiplier tube? When I talk about the photomultiplier tubes, the photomultiplier tubes are having the high resistance. The advantage is having the high resistance, particularly up to 1 lakh volts we can use as an external resistance. So this is the major advantage of photomultiplier tube. So it is similar to your phototubes. In phototubes, what we have done, we have passed the light radiations and they are hitting the photoemissive cathode. Here also we are keeping the photoemissive cathode, which is made up of cesium oxide, silver oxide or potassium. Now once the photons are converted into electron, now this electron is emitted here. Say for example, if one electron is emitted here, this electron is coming and hitting another important object called dynode. So dynode, what are these dynodes? The dynodes are the positive electrodes which is made up of either gallium or antimony or phosphorus or chromium ion, which is having special sensitivity to attract the electrons. So this is the purpose of any dynode, right? So in this particular thing, in the phototubes we have seen that only we are having the photoemissive cathode, then we are keeping the collector anode. But here between the photoemissive cathode and the collector anode, we are keeping around 8 to 10 dynodes in between. Right? We are keeping 8 to 10 dynodes in between. So what is the purpose of these dynodes? The dynodes are having the capacity, because the material coated in the dynode is either antimony or gallium or phosphorus or chromium ion. These elements are having the special affinity to attract the number of electrons, as well as they will try to multiply the number of electrons. Right? They have more sensitivity towards the electrons, as well as they will try to multiply the number of electrons. So that is the reason the principle is nothing but multiplication of photoelectrons by secondary emission of electrons. We will discuss how it is taking place. So if you look at that, when the light radiation is hitting the photoemissive cathode, say for example, if only one electron is emitted here, when it is hitting the first dynode, this one electron will be multiplied into 5 electron. For example, when it is hitting the first dynode, they will be converted into 5 electron. Now when they are hitting the second dynode, the 5 electron will be multiplied into 25 electron. And when they are hitting the third electron, the 25 electron will be multiplied into 125 electron. So like that, there is a multiplication of electrons taking place in a cascade signal. Why we are having this type of multiplication? And every dynode we are keeping some difference in potential. Maybe the first dynode is having 75 volts potential, the second dynode is having 150 volts potential, and the third dynode is having 225 volts potential. So each and every dynode differ in a potential of at least 75 to 100 volts. That is the reason one electron will be multiplied to 5 electron, 5 electron will be multiplied to 25 electron, and 25 electron will be multiplied to 125 electron. Finally, all the shower of electrons will be collected by the ring anode or the collector anode. So this is how there is a photo multiplication of secondary electrons. That is the major principle of photo multiplier tube. We can say that the multiplication of photoelectrons by secondary emission of electrons. So the electrons are getting multiplied and finally the shower of electrons will be collected by the collector anode. So this is how we are measuring this photo multiplier tube signal intensity, right? I hope it is clear. The only thing we are using in a single instrument, we are using 8 to 10 dynodes. They are little costlier, but they are mostly used in double beam spectrophotometer, UV visible double beam spectrophotometer. So most of the modern instruments are having this photo multiplier tube as a detector. Now, what is an advantage of this photo multiplier tube? Even very weak signals can be amplified better. Particularly in case of fluorescence, you will be getting a very weak signals. So when you have weak signal, what will happen? The weak signals, when you are having the weak signals, if you use either barrier layer cell or phototubes, you will not get proper measurement of the signal intensity. So in that case, we have to use photo multiplier tube because they will multiply the number of electrons and finally all the electrons will be amplified by the ring anode here, right? So this is an advantage of this photo multiplier tube, which is very widely used in UV visible spectrophotometry. And another important thing, the amplification factor is calculated by the formula n power d, where n is the number of dynodes, n is the number of electrons and d is the number of dynodes, right? So this is the formula used for calculating the amplification factor for photo multiplier tube. And the last important detector used is silicon photodiode, right? So they are not having specificity because silicon photodiode is basically a semiconductor based detector, and we can use this detector in the wavelength range from 190 nanometer to 1000 nanometer. That is in the sense from UV region to visible region and to infrared region, particularly near IR region. Up to that range we are using this as a detector. So semiconductor detector is basically silicon photodiode detector. So how this detector is coming into force? I will give a simple example here. If you look at here, we are showing some energy gap here. There are different bands I have put here. So these are all the various energy bands produced in the solid, right? And there is a band gap here which is called as Eg. Eg is called as energy band gap, right? So what is called valency band? First of all, you should know what is the meaning of valency band. Valency band is the highest band that is at least partially occupied by electrons. Valency band is the highest band. Say for example, this is the valency band. The valency band is the highest band which is at least partially occupied by electrons. And the energy band immediately above the valency band is called conduction band. After valency band, you will be having another band. That band is called conduction band. Okay, suppose if this is the valency band, this is the valency band, right? This is the valency band and this is your conduction band, right? So what I mean to say, valency band is the highest band that is at least partially occupied by electrons, whereas conduction band is the energy band immediately just above the valency band. And both these bands are separated by a forbidden energy range. Forbidden means a very less energy range, that is called Eg, and that is called band gap. There is a band gap existing between valency band and the conduction band, right? If the valency band of a solid is completely filled at a temperature of 0 Kelvin, if the valency band of the solid is completely filled at a temperature of 0 Kelvin temperature, the material is called either semiconductor or insulator. Is it clear? Suppose if the valency band is partially filled, then the material is called as a conductor. Very simple thing. Is it clear? If the valency band of a solid is completely filled at a temperature of 0 Kelvin, the material is said to be either semiconductor or insulator, right? So when I talk about which is semiconductor and which is insulator, there is a minute difference between the semiconductor and the insulator term. If the band gap or the energy band gap is less than or equal to 2.5 electron volt, then it is called semiconductor. The material is said to be semiconductor. Suppose if the energy band gap is greater than 2.5 electron volt, then the material acts as an insulator. So this is a minute difference. So when the band gap is less than or equal to 2.5 electron volts, it is just acting as a semiconductor, whereas if it is more, it acts as an insulator. Now, most of these elements, the semiconductor only we are using as a detector. So which type of elements are used as semiconductors? Basically silicon and germanium are the elements used as semiconductor materials. They are called as intrinsic semiconductors, inbuilt semiconductors. And there are some other materials also we are using, say for example gallium arsenide, cadmium telluride. These are also other examples of semiconductor materials. Now these intrinsic semiconductors, they are the semiconductors. If you want to increase the conductivity in the semiconductor, we just add some doping agent. And these doping agents we can choose either from 5A element of the periodic table or 3A element of the periodic table. The 5A elements are arsenic and antimony, whereas 3A elements are indium and gallium. If I add the doping agent arsenic or antimony with the silicon or germanium, so what will happen? The intrinsic semiconductor, along with the intrinsic semiconductor, we are adding this extrinsic material, right? Arsenic or antimony. So if I add this thing, what will happen? Automatically the conductivity is increased as such. Electrical conductivity will be increased and you can use them as a detector. This is an idea, right? Particularly they have if I add these 5A elements as a doping agent, if you are using as a doping agent or dopant means mixing. You are mixing this thing with the intrinsic semiconductor materials, right? So if I add this arsenic or antimony, what will happen? They have an extra electron as such. Suppose if we use indium or gallium and mixing with silicon or germanium, in that case they have particularly you have this electrons, missing electrons. They generate the missing electrons. Here they generate the extra electrons, here they generate the missing electrons. Based upon this phenomena, we just add and try to increase the electrical conductivity from one band to another band for acting as a semiconductor device or a detector as such. Now what is this diode? We are using silicon photodiode, right? As we are using semiconductor materials here, what is the purpose of diode? Diode is basically a rectifier which permits the current to flow in one direction. Okay, the diode permits the current to flow in one direction. So we are using linear photodiode array, or we are using the photodiode array as a detector. So we are keeping many diodes as such, and they have different junctions followed by P junction and N junction. So PN junction will be there, right? So a PN material or PN junction will be attached. As such, alternatively P junction followed by N junction, again P junction followed by N junction. Like that we are making this diode in a linear manner. Either they work in the forward bias or in the reverse bias direction, and they are useful as a semiconductor detectors. Even though their sensitivity is less, they are useful for the wide range from 190 to 1000 nanometer. So this is all about the various detectors we are using in UV visible spectrophotometry. I hope you understand in a better manner. Thank you very much. Thank you, my dear students. Thank you.